Hello friends, so today we are going to complete the last testing of our chapter, that is the mechanical properties and the testing. So this is the last testing of this particular topic. So the creep test, that is the very important, again the testing of the material. So creep testing or creep failure is the very interesting thing because basically that particular creep failure, it is related to some sort of that plastic deformation. Now you may say that already we have seen that plastic deformation is occurring in the tensile test, and then what is the then difference between that particular creep failure and tensile failure. So it is very interesting to see what is the meaning of creep and what is the creep failure. So basically, first of all, we will just go with the creep. So creep is the time dependent process where a material under applied stress exhibit a dimensional change at a high temperature. So this particular term is very much important, that is the high temperature. So basically in case of tensile stress is again some sort of the time dependent process where we are applying the load on that particular component, but that particular load is not dependent on any kind of that temperature. So here in case of creep, we are applying the or this particular test we are conducting at a very high temperature. So this is the high temperature progressive deformation of a material at a constant stress. It is called as a creep. So this is very important, high temperature progressive deformation. So progressive, or you may say that is the plastic deformation of material. So at a constant stress, so whatever may be the load we are applying, it is constant. So it will be at a constant stress, but we are conducting this particular test that is at a high temperature, so which is very important. So it may be create some confusion in your mind, that is what is the tensile, what is the meaning of creep. So in the previous first lecture of this particular topic, I have explained about the tensile testing. So you can be able to go with that particular lecture, and then you just watch this particular lecture. You will understand what is the basic difference between the creep and the tensile stress. So in that tensile stress, that is not dependent on the temperature. Creep, it is dependent on the temperature, that is the high temperature. So that particular deformation, it is carried out at a high temperature. So the process is also the temperature dependent. So along with the time dependent, it is just a temperature dependent process. So which is not there in the tensile stress. So creep always increases with the temperature. So this is very much important. Now, how does the creep is occurs? So basically the creep occurs when the vacancy in the material migrate towards the grain boundaries that are oriented normal to the direction of the applied stress. So basically when we are having a very high temperature, so basically the vacancies are creating in the material because it has been start to the deform after the melting point. So those vacancies in the material, that is migrated towards the grain boundaries. So those vacancies are migrated towards the grain boundaries, and that are causing some sort of that crack formation. So creep can be occur due to the different mechanisms. Now what is the threshold of the creep? So the critical temperature for the creep is the 40% of the melting temperature. So if suppose the melting temperature is 1000 degrees Celsius, so whatever may be the critical temperature for the creep, it is the 400 degrees Celsius. So here we can be able to see, that is if the temperature is going above the 40% of the melting temperature, here we can be able to understand, suppose the melting temperature is 1000, so 0.4 into 1000, that is the 400. So if the temperature is going above the 400 degrees Celsius, the creep is likely to be formed. So that is the vacancies are going towards the grain boundaries. So that is called as the creep formation. So in that particular thing, only the thing is happening is what? That is the vacancy in the material that are migrating towards the grain boundaries. So that is called as a creep formation has been occurred. So this is just a general threshold for the creep. Now the mechanism of the creep, how the creep has been formed, that we will see. The different mechanisms are responsible for the creep in a different material and under the different loading and temperature conditions. So the mechanism includes the stress assistant vacancy diffusion, the grain boundary diffusion, the grain boundary sliding, dislocation glide, and dislocation creep. So these are the different mechanisms are there. Because of those mechanisms which is responsible to form a creep in a different materials. So basically that has been under the loads, different loads and different temperatures. Okay. So the high temperature creep. So basically what is the meaning of high temperature creep? So the atoms move faster in that particular high temperature creep. So if the temperature is high, the greater mobility and dislocations will be there. Then increased amount of vacancy. If the temperature is very high, the vacancies maybe get increased rapidly and those vacancies are moving towards the boundaries, grain boundaries. So the deformation at the grain boundaries may be occurred. So whatever the metallurgical changes are there, so the phase transformation, then the recrystallization, it may be occurred. So the high temperature materials that improves the high temperature strength and good oxidation resistance. So if the temperature is going on increasing, it may be create a creep in that particular material. So what is the effect of high temperature on the metal? Basically, it will be lower the strength, then the greater atomic and dislocation mobility, then high equilibrium concentration of the vacancies. If the temperature is increases, what will be the happen with the material or metal that is given over there? If the temperature is high, then that metal lose its strength, that is lower the strength, then the greater atomic and dislocation mobility, assisting a dislocation claim and diffusion, then high equilibrium concentration of the vacancies. If the temperature is going on increasing, the higher equilibrium concentration of vacancies are there, then no deformation mechanism such as new slip system or grain boundary sliding, then the recrystallization and grain growth it is there, and the oxidation and interregular penetration. So these are the effect of high temperature on the metals. So how that creep testing is carried out here, it is a generalized diagram. So here you can be able to see this is the component which is loaded. So this is the load applied and this has been kept under the furnace. So this will be increasing the temperature. So whatever maybe this yellow color has been shown, that has been provided or increasing the temperature of this particular specimen. So usually we are taking the tensile bar. Similarly, like a tensile test arrangement, you can be able to see over here. Then the dead loads are applied. Then strain is plotted with the time and test is usually end with the rupture, that is the creep failure. So temperature is increasing and the component has been gets failed. So that is called as a creep rupture. So this is again the generalized line diagram, how the components are there. It has been arranged, how that remaining mechanism is required. So this will be a top plate. So this is the furnace we are required. This is the component. So this is the lower pull rod. This is the universal coupling, and then the loading weights are there. So this is the generalized figure of for the creep testing. Now this is the exact machine, that creep testing machine, how that machine it is there, you can be able to see. Again in the video we will see how that exactly the creep testing has been carried out. Now, after the creep test, what exactly will be there? So basically, the constant stress versus time dependent phenomena it is there. So sample deformation at a constant stress and time. So here you just see this particular diagram, or we can say that graph. So this is the creep strain versus time. Okay, so this will be a strain will be goes on increasing at this side, and time will be goes on increasing. So this particular that graph has been divided into the three phases. Here the primary phase, this will be a secondary phase, and this will be a tertiary phase. So in the primary creep, the slope decreases with the time. Whatever the slope it is there, that has been decreases with the time. Then in the secondary creep, the steady state, that is the constant slope, the most of the slope is constant over here, strain is not much increasing, and time will be also, the time is also increasing. So strain and time is constantly increased, and in the tertiary creep the slope increases with the time. So here the slope will be goes on increasing. So here the slope is decreases with the time phenomena, here the constant for the secondary phase, and at the tertiary phase again that slope will be goes on increasing. So at that particular point, this rupture, that is the failure, maybe gets occurred. So this is indicating with the TR, that is the time for the rupture. So these are the some three stages. So primary, or it is called as a transient creep. So in that slope of the strain versus time decreases with the time. That is work hardening. Then for the secondary, that is called as a steady state creep. So just words are quite similar, that is the primary, or it may be called as a transient. So basically the deformation is elastic. Then secondary, or it is called as a steady state creep. So in that steady state creep, rate of the straining is constant and the balance of work hardening and recovery. In the tertiary, that is called as a rapidly accelerating strain rate up to failure. So formation of internal cracks and voids, grain boundaries, separation, necking, etc. is formed in this particular phase. So basically the internal cracks are developed in this particular phase, then voids may be occurred, and basically the necking has been formed. Now these are the some temperature effects, stress and temperature effects on the creep. So this will be a T1 or sigma 1, this will be a T2 or sigma 2, this will be a T3 or sigma 3. So basically when the T1 is greater than the, sorry, T2 is greater than the T1 and T3 is greater than the T2, how that slope has been formed. So if the temperature is very higher, the rapid slopes it will be there, and if the temperature is below the threshold temperature of the creep, that is 0.4 into melting temperature, if the temperature is below, then there is no any rupture it is there. So here we can be able to see the strain is constant and time is constant. So if the temperature is going on the increasing, then the rupture will be occurred. So when we are increasing the temperature, here we can be able to see the T, it is at the lower side of that threshold temperature of the creep, then T1 is increased than that of T. How the rupture will be occurred? If again we are increasing the temperature, the stress will be increased and rupture will be shortly occurred. So it is the time dependent phenomena. So within the short period of time that rupture will be occurred. And here again if we increase the temperature, again within the very short span of time the rupture will be occurred and strain rate will be faster. So creep fracture or stress rupture. So basically the stress rupture testing is very similar to the creep testing, except that the stresses used are higher than in the creep test. So the stress rupture testing is always done until the failure of the material. So that is the stress rupture testing. So it is very similar phenomena with the creep testing. There is not much difference. So this is how the changes are exactly occurred that has been shown. So this is the crack formation. Here we can be able to see the grain boundaries, and here this particular locations we can be able to see how the cracks has been developed. So this is the graphs, SEM graphs. So here at the red color we can be able to see this will be a crack formation. So the realistic image also we will see. So if the intergranular creep fracture it is there, so here we can be able to see. So this is a transgranular creep fracture, and this is the internal granular, means at the inside of that particular component. This is the transgranular, means it is not depends on the grain boundaries. At anywhere that crack has been formed, it is not dependent on any grain boundaries, so that is called a transgranular creep fracture. And this is dependence on the your grain boundaries. So whatever may be the crack formation it is there, here you can be able to see this is all dependent on your grain boundaries. So these are the grain boundaries, and exactly the crack is developed on that particular grain boundaries. So it is called as an intergranular creep fracture. Only the two, transgranular and intergranular. Now, what is the stress versus rupture lifetime? So this is the general graph when we are going to study the effect of the creep. So this kind of that graph we have to study, that is the how much is the stress, how much is the temperature. So rupture lifetime, how much the whatever the stress has been increased, then what is the effect of the temperature on that. So that has been shown. So it depends on the creep strain rate or stress versus structure lifetime for low carbon nickel alloy at a 3 temperature. So that has been shown for the low carbon alloy. So how it is just a practical graphs. Now the creep failure, now how the exact SEM image are there. Here we can be able to see the cracks. Okay, so here we can be able to see the cracks are formed, and then that particular, this will be an intergranular. So this is again the crack. Here we can be able to see the cracks form. Here again the cracks are we can be able to see. So on that microscope, here we can be able to see the cracks. So on the heavy microscope only we can be able to observe such kind of that cracks. So these are the creep failures, how the creep failure is occurred. But this kind of failure is not there in the tensile test. Exactly the component has been breaked. We are no need to study under any microscope and all. But in case of creep formation, these kind of that cracks, internal cracks, are formed under the high temperature. So this is the practical images, okay, of how that crack has been formed and how the failure has been occurred. So here we can be able to see that particular crack for the machine. Now the creep failure are characterized by the things, that is for the strain the tube, the thick edge fracture often with a very little ductility, intergranular wide cracks in the microstructure we can be able to observe. So these are the some characteristics of the creep. Now to avoid the creep failure, what we have to do, that is creep is generally minimized in the material with a high melting temperature. So we have to choose the material such as which is having the very high melting temperature, then high elastic modulus. So that particular material should have the very high elastic modulus and large grain size. So for that particular material, it should have the very large grain size. So material which is especially the resilient to the creep are the stainless steel, so which is having the very high resilient to the creep. Then refractory metals that is containing the element like NbMO, then tungsten likewise. Then superalloys, that is cobalt, nickel based, some sort of that, which has been performed the hardening operations. Then the single crystal turbine blade. So here we can be able to see some sort of that realistic components which gone under the very high temperature failure, that is creep failure. Now how that particular creep test has been conducted, here we can be able to see. The capacity of this particular machine is 10 to 2000 kilonewton, 200 kilonewton load we can be able to apply. Now this is the furnace, which is having the range of 1300 degrees Celsius. Okay, now this is the component. These are the heating rods what he have applied over here. These are the heating rod. So whatever may be the heat from the furnace, that has been transferred through this heating rod to the component. Now some sort of that software based operating system is there. Now we have to set some parameters, so which is not required to apply manually. Through the software we can be able to put all those required parameters in the software itself. Now that graph automatically we are getting. So three stages I have explained, that is primary, then secondary and the tertiary. Now after basically that working temperature is 300 to 1300 degrees Celsius. Now we can be able to set some steps points for the temperatures. Now this is the generally the component which can be able to used over there. Now the constant heating process is going on. These are the extensometers which are used to apply the heat. Now the specimen here we can be able to see this specimen has been broken. Here we can be able to see after applying that much heat the specimen is broken, so that failure is occurred, but this particular failure is due to the creep because of that high temperature. That dislocation is appeared, void spaces are generated, and because of this the specimen is broken. So I think you have just cleared about the creep and creep failure. So I hope you have just understood the things nicely, and this is all about the second chapter.